Hi everyone, to see some essential definitions that will be needed when we want to deal with functions of complex variables. So our goal is to discuss about elementary functions. And first we want to discuss some definitions that will be essential to define functions of complex variables. So we want to discuss some definitions. So let's see. The first definition will be of a neighborhood. So let me write it down. We want to define something called a neighborhood. So what is a neighborhood, right? So neighborhood. So let's say you have a complex number z0 and you want to define a neighborhood of this z0. So let's say we have z0 and the neighborhood of this z0 is defined like this: z minus z0 is less than epsilon, where epsilon is greater than 0 but sufficiently small. And what is this z? Well, you can define a circle. Let me try to draw this. Let's say this is a circle and this circle is centered around z0. Okay, and let's say z is any point on an outer circle like this. Okay, so z can be any point over here, and this means that the distance from z to z0 should be less than epsilon. So this green dashed line can be a neighborhood of this z0. So if you want to view this more accurately, you can draw the real and imaginary axis and you can draw two vectors from here, one that corresponds to the position of z0, another one that will indicate any point on this circle. It can be over here, it can be over here, 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 so on and so forth. And this distance, let's call it r. That means the distance between z minus z0 is equals to r. That is the radius of the circle that is indicated by this blue line. Now you can draw another circle that's radius that has a radius less than this r. So if you draw a circle like this, this is a neighborhood. Let's call this epsilon 1. You draw, let's say, another circle like this. This is epsilon 2. This is another neighborhood. So this is what we mean by a neighborhood. You draw a circle with very, very small radius, and that is defined as the neighborhood. And after neighborhood, there is another kind of neighborhood, or let's say another kind of region, though we haven't defined what is a region so far. There is another kind of thing that is called an annular or annulus region. So mathematically this is defined like this. Let's say you have two circles, one of them has a radius r1 and the other has a radius r2, and any point z0, both of these circles are centered around z0, and the annular region is defined like this: r2, where r2 is greater than r1, obviously. So let's say this is our z0. This is circle 1, has a radius of r1, and this is circle 2 that has a radius of r2, and this in between region, this is the annular region. Okay, now that we are done with the definitions of neighborhood and annular region, or let's say annulus, whatever you want to call it, let's move on to another important definition, that is interior points. So what are interior points? Let's say you have a set S like this, then a point Z0 will be an interior point of S if you can draw a neighborhood around this Z0. If you can, I'm saying draw, but this actually means that if you can define a neighborhood. Okay, so if you can draw a neighborhood of Z0 that is entirely contained within S. If you want to see it graphically, let's say this is our set, some set S, and what are the interior points? Well, let's take a point over here, let's call it Z1. If I can draw a very small neighborhood, and inside this neighborhood all the points are contained within S, so this type of points will be called an interior point, like this one. However, if you consider a point over here, let's say like this, you can already guess that this is like a boundary, and then if you draw a neighborhood, that means you draw a very small circle. No matter how small it is, as long as this epsilon thing that we discussed over here, that means the radius of the circle, if it's greater than 0, some of the points will lie outside this set, so this is not an interior point. But this one is. So this is an interior point, and from this definition of interior point and from this picture we can come up with another definition, and that is the definition of the boundary points. And these boundary points are these points, this one right over here, that you take a point and then you draw a neighborhood, or you make a neighborhood, and you see that some points are inside this set and some points are outside this set. If a point exhibits this kind of behavior, you can call those points boundary points. So how do you formally define it right now? Is that for any set S, let's say set S, if there are points that includes by points by point that includes, what I mean is that the neighborhood, the point's neighborhood, that includes at least one point in S and at least one point that is not contained within S. That means if there are points that includes at least one of the points that is inside S and one point that is, okay, let me just draw a line over here so that you can understand, that is outside S. These points are called boundary points. Now let's define another thing that is called an open set. You already know about it, but we can also define open sets in terms of interior points. So what are open sets? If you have a set and all the points of that set are just interior points, then that is called a open set. So for any set, let's say now K, if all the points are interior points, that means there is no boundary point, right? Because all the points are interior points, then they are called open set. Now what is a closed set? A set that is not open. Defining closed set from the definition of open sets are simple, so I'm not going to write it right now. So we have defined these points, these sets. Now what we can do, we can use all these definitions and we can define something called a region. That will be of special interest later. So the definition of region: if you have a set, let's say K, let's say set K, and if this set K consists all points of an open set, if it consists of all points of an open set, that means you have an open set, that means all the interior points, okay, then in addition it will carry some, none, or all of its boundary points. Then it is called a region. So what do we mean by this? So let's say you have this set K, okay, and visually let's say this is how you want to visualize set K. Now even though this is a solid line, that doesn't mean this is the boundary. I can even draw it with a dashed line as well, just to indicate that there is no boundary and stuff. That means there is no boundary of this set. So this can be thought of as a region, the thing that I just draw with that dashed line. So this is a region. Why? Because it contains all the interior points, that is points like this over here, interior points, and since this doesn't have any boundary points over here, they're also interior points, okay. And then the definition is saying that it should contain all the interior points of this open set. Then it's saying that it should also carry some, none, or all of its boundary points. So let's now assume that we have a boundary like this, take one, yeah. So this is our boundary. If your set contains all these boundary points as well, that is all the points on the boundary, some of it, all of it, or none of it, then it is also called a region. So this whole thing can be thought of as a region. Now let's say this is the boundary and this is the whole set, right? Can we make another region like this? Let's say this is one point over here. Let me use another color. This is one point over here, and then I'm just using this one, right? I can also make a region like this, so on and so forth. So this is a region. That's what the definition tells us, the thing I just drew in the picture. Now there can be different kinds of region, and we are mainly interested about bounded and compact regions, so let us define those things as well. First we want to define what are bounded regions. So a set consisting all of its point, as I said before, if it contains all the all the interior points of an open set and some, none, or all of its boundary points, then that is a region. But if you have a region and there is a constant, let's say k, okay, let's not use k, let's say gamma, a constant, and our set is set under consideration, or set of interest is k, then for all the points in set k, if those points are less than this gamma, this is a constant. Now this set k will in general carry complex numbers, right? And how we can get a measurement of the absolute value of a modulus complex number? That is just the modulus thing, right? For all z belongs to k, if z is less than or equals to gamma, then this is called a bounded region. Okay, but we also have to consider another thing. Let's say what type of region that would be. I mean, we are calling it a bounded region, but is this region open, closed, or what, right? That's the thing we have to specify. So what you need to do is that first you say that, okay, let's deal with the open regions first, and you say an open region is said to be bounded if we have a constant gamma, and for this gamma constant all the points inside, that is inside this region, will have to satisfy this inequality. Okay, that means let's say you have a region like this, and let's say this is our region, let's call it R, that's the notation, and let's say this gamma thing is defined on a circle like this. So any point you can take, by any point I mean any points modulus you can take, will lie inside this region, and they are obviously less than this gamma. This can be thought of as a zoomed in picture. So that is the definition of a bounded region. Sorry about that. Now we have said this is only for open regions, so what about the closed regions? Can there be anything as a closed region? Well, yes, it's pretty simple. If your region contains all the boundary points, then it's closed. Okay, so this is not a separate definition, but a definition that comes within this bounded region stuff. So if a region contains all of its boundary points, then it's called a closed region. There we have it. And now using this definition of closed region and bounded region, we can define the compact regions. So if you have a region that is closed and bounded at the same time, those are called compact regions. So compact regions are closed plus bounded. That means it's such a region that is bounded by some constant, and at the same time it contains all the points of its boundary as well. So that's a compact region. Now we are almost done with our definitions, so let's define one or two more things. Now let's say you have a region like this in a complex plan, or you defined a region like this and you take some points. Let's say you take this point z1 and you have a point, let's say z2, and now you want to see whether you can connect these 2 points by some broken lines. So these are our broken lines. Okay, these are the some, I don't know, z3 4 5 6, like this. So our main goal is to connect this z1 and z2, and if this is possible on a region, that means you can connect any 2 points with the help of some broken lines without any discontinuity, then this type of a region would be called a connected region. Now if you make a cut over here somehow, then you would not be able to join z3 and z4. So in that sense, z1 and z2 won't be connectable via these broken lines, and hence this won't be a connected region. Okay, and an example would be, that means an example of this disconnected region would be a region, let's say, that is bounded by modulus of z equals to 1. That means there is a circle of radius 1 and there is a circle of, let's say, okay, let me use another color to signify this thing. Yeah, let's say this is z2, we can also call it z1 z2 whatever, and a disconnected region, see this thing, that if this is our region of interest, this one, that is something like an annulus, we can obviously define points over here and we can connect them like this. But if we have a point over here, let's say this is w1 and there is another point exterior to this z modulus of z equals to 2 circle, let's say w2, we cannot join these 2 points with the help of the broken lines, because you would have to cross this boundary and stuff. So we cannot join them with the help of these broken lines like this, and hence they are disconnected with each other. Okay, so this would be an example of a disconnected region, and mathematically you would express them like this. So this is just a mathematical expression that are interior, this z, or you can also say w as well, this w is such a point that is bounded by this, that is interior to this circle, this lighter green, that is circle with radius 1, and exterior to circle with radius 2. Now one important thing while discussing functions, whether in real or complex variable, is the topic of thing called a domain. And domain is what? Well, a connected open region is called a domain. It's as simple as that. So what is a domain? It's a connected plus open region. That means you have some region like this, okay, it doesn't have a boundary and it's connected, and this type of region would serve as a domain. So the domain doesn't have any boundary points, and the reason I'm emphasizing this is that, let's say you want to define a domain for some functions. Let's take the very simple bookish example like this. Some function, let's say f of z is equals to z, and z can be represented with this polar form. Then if you fix this r, then for theta you are defining it like this, where theta 0 and alpha, they're just some constant or numbers, whatever you want to call them. So as you can see, these are the boundary points, and the domain, that means the values theta can take, don't include them. So there is this idea of this openness. Okay, and all the values theta can take, they can be connected with broken lines. That means you can add things up to shift from one place to another for different values of theta. So this is the domain thing. Now domain is an open set, and we note that no boundary point of the domain can lie in the domain, because why? Because this is an open thing. Okay, and we have used the notation R to define a region. You can use any other notation you want. And the closed region, if this represents some open region, the closed region would be generally denoted by this R bar. Okay, now we have defined domain. Now we can go on and define a function. Now there is a subtle thing here. The functions that we will be discussing right now, all of them will be single valued functions. So let me just write it down. Why single valued only? Well, in the case of complex variable and multi-valued functions, additional complexity arises, things like branch point, branch cuts, and so on. So that's why we don't want to discuss it right now. We will see them later, in the later phase of this course. So with that in mind, all our functions will be single valued. So let's keep this in the back of our head and move forward. Let's say you have some z, a complex number that belongs to some region. That means this is the domain, an open region, right? Because in the definition of domain we said that it's open and it's connected, and the open regions we denote it with just R. Let's say for each z in this R, that means you have a region. For each of those points in that region, you have another unique complex number. We get, okay, let's write it down. For each z that belongs to R and domain or open region, whatever you want to call it, we get another unique complex number w of z, or you can call it f of z, whatever you want to call it. Let's call it f of z so that everyone can understand. F of z. Then we say that this f of z is a function of complex variable z. So this is the definition of a function of a complex variable. Okay, and so far we are only considering the single valued functions only, and the values f of z that correspond to z belongs to R over here, they constitute the range of f of z. That means all the values you can have, since we are already assuming that all the values are uniquely determined, all the values you can have, you put them up together, you get the range. Okay, an example would be, let's say f of z is equals to z to the power m, or f of z is equals to, let's say, az cube, stuff like this. So yeah, this is the definition of function. Now what you can do is that you could write z as x plus iy in this format, right? So what is the format of this f of z, you ask? That in terms of the Cartesian coordinates or the polar coordinates, how can you write that? Well, let's take a very simple example. Let's say f of z is equals to z square, where z is denoted as x plus iy. Let's see, let's do this algebra, small algebra, and see what happens. So this means this is x plus I whole square, right? So if you expand this, this is just x square minus y square plus 2ixy. So you can already see that this is a multivalued function. I mean, by multivalued I mean there are two variables, x and y. Okay, so you can write them as u of xy. This is the standard notation, and you can pick out this I and write this 2xy thing as vxy. So in general this thing also holds. That means for this representation you can write this function of a complex variable in terms of x and y such that there is this real part and there is this imaginary part. Okay, what about r and theta? What if you do r and theta, right? Let's try to take this example as well. So now let's see the polar thing, what happens in the polar format. So you have this f of z is equals to z square. You write this e to the power I 2 theta. Now you can expand this e to the power I theta in terms of sines and cosines. So this would be just cos 2 theta plus I sine 2 theta, and as you can see this is a function of r and theta. You multiply this whole thing with r. You can easily see that there are two parts, one of them being real, one of them being imaginary. And now you can write this as, let's say, capital U. You can use other notations if you want, it really doesn't matter. Capital B r theta. So yeah, you just use the representation, and you can see that in both of these cases, when you represented z with x and y's, f of z came in terms of u xy plus I v xy. I mean small v. You represented z in terms of r and theta, f of z became some functions of r and theta in the real part, and in the imaginary part the same variables appeared. So this is again the real part and this is the imaginary part. So this will be it for today, and I'll see you guys on the next lecture. Thank you.